All right, so today we're going to be talking about the law of conservation of energy. This is going to be a little bit of a throwback from physics last year. So just to remind you that when we have any chemical or physical process, energy is not created, it's not destroyed. It's a transfer of energy from the systems to the surroundings, or maybe from the surroundings to the system. And energy can change forms. Potential energy can convert into kinetic energy or to sound energy and different forms of energy, heat energy, etc. So let's talk specifically about heat. So heat is energy that transfers from one object to another based on a temperature difference between them. It's represented by the letter Q. And we're always going to flow from warm objects to cool objects until the temperature of those objects or those two zones are the same. The fancy way for describing that is thermal equilibrium. Okay. So when we have heat transfers or changes, when heat goes from system to surroundings or otherwise, we have two words to call it. So we call it endothermic and exothermic. So in an endothermic process, the shift is going to be heat is going to go from the surroundings into the system. So the system is going to gain heat as the surroundings cool. We're going to have a positive Q value for that. For exothermic process, it's going to release heat to the surroundings. So the system is losing heat and the surroundings are heating up. And so we're going to assign a value of a negative sign for our Q value. So one way to remember this is endo is like the word enter or in, okay? And exo is like the word exit or to go out. So we use a systems-based approach. So we define the system using these two words. So endothermic process, heat enters into the system. In an exothermic process, heat exits out of the system. All right, so let's try that. So we've got an example here. We've got a cold pack and we've got a person who is using that cold pack. So what we're going to do is we're going to draw some arrows to show the flow of heat. So in this case, the heat is flowing from the person's body into that cold pack. So the heat is going into the cold pack. And we're going to define the cold pack as the system. And so we're seeing a shift from the surroundings to the system. Oh, I didn't spell that great. Okay. So this would represent an endothermic process because heat is going or energy is going into the system. Okay. We're going to assign that a positive Q value. So this would be Q plus because the potential energy is going up as energy is going into the system. Let's see another example. So if we have an example of a campfire, and I like to situation myself out here, I just have to remember that I am the surroundings. Okay. So if we're going to draw some heat flow arrows, the energy is going from the fire out into the surroundings. So the energy is transferring from the system, which is the fire, to the surroundings, which is me and it's the air and it's all those things. So this would represent an exothermic process because energy is exiting the system. Okay, and our Q value would be negative. Okay, so the energy is potential energy is going down in the system. Great. So I like to do this demo here. So I've got some magnets, and these are going to represent like molecules in a bond. So it's a little bit of a stretch, but it's a good one. So if we think about two atoms that are bonded together, these would have a relatively low potential energy, okay? When I separate them, when they're far apart from each other, they're going to have a higher potential energy. So when we separate them, they are going to be a high potential energy. Okay, so the process of going from a low potential energy to a high potential energy, energy must be going into the system. Okay, so it requires energy to break the bonds in a reaction. Okay. On the opposite, if we start with a high potential energy situation where, say, the magnets are farther apart and we bring them close together, they will snap together, okay? They're going to release energy as they go from a high potential energy system to a low potential energy system. The energy is flowing out of the system, okay? So this would represent an endothermic process. Energy is going in, and this would represent an exothermic process. Energy is overall going out. So let's talk about this in terms of some terms, and we're going to apply this to some graphing. So our potential energy is that energy stored in bonds, and it's energy needed to break the bonds. Energy is given off when bonds are made. Again, we're going from a higher potential energy system to a lower potential energy system when they're bonded together, okay, versus going from a low potential energy system to a higher potential energy system, okay? Activation energy, we'll talk about in a second, but it's the energy required for a reaction to occur. So there has to be some amount of energy that is present that will get the ball going and allow the reaction to occur, okay? We use the term the enthalpy of the reaction to describe the overall change in energy from our reactants to our products. So let's see what that looks like on a potential energy diagram. So the first thing that we have is we've got the potential energy of the reactants. And that's going to be what we start with. So the potential energy of the reactants, in this case, is just going to be 50 kilojoules. How much energy do we start with right here? Okay. The potential energy of the products is how much energy do we get at the end? Okay. So if you look on our graph, the potential energy of our products in this example would be 100 kilojoules. So we just track this back to see that it is 100 kilojoules. Okay. Our activation energy, EACT, is how much energy do we need to get the reaction going. So the thing we're going to do is we're going to see how much total energy needs to be used, and then how's that different from where we start. Okay, so we're going to see what's the difference between the reactants and the top of this curve. So we increased by 200 kilojoules in order to have the reaction begin. That's the activation energy, the energy that we need to put in to allow the reaction to go. Okay, so comparing the reactants to the top of that activation energy curve. Okay, and then the last thing is the heat enthalpy. Okay, the heat enthalpy is the overall change between the products and the reactants. So you're going to do products minus reactants. So when we do that, we can see that we go up by 50 kilojoules. So the way we did that is we did 100 kilojoules minus 50 kilojoules equals positive 50 kilojoules. For our heat enthalpy, we do need to indicate a sign, either plus or minus. So you can see here how the graph increases. The product's energy is greater than the reactant's energy. And so that's where we need that plus sign to say that it's increased by 50 rather than decreased by 50. Okay. So this is an example of showing that energy increase. Because the products is greater than the reactants, we know that energy goes into this reaction, and this would represent an endothermic curve. All right. This curve, when we compare the reactants to the products, overall the energy goes down. So this would have a negative delta H, and this would represent energy leaving or going out of the system. So that would be an exothermic process. So side by side, you can see the difference between an endothermic and an exothermic reaction. Please note that in this example, we kind of eliminated the activation energy, but the activation energy would be above in each. I'm just kind of sketching what it might look like if we put it back in blue. Okay, you would see that still hump up at the top for each.